Hello student, in the last lecture we have to seen that we complete exercise 1.1 which is depend upon derivative of a composite function. Now today we are going to start the second article of the differentiation, that is a derivative of inverse functions. So we consider here y equal to function f of x. If this function is 1 1 and onto, then its inverse function x equal to f inverse y is exist. So if the function y equal to f of x is 1 1 and onto, then its inverse function x equal to f inverse y is exist. And if this inverse function is exist, then it is a differentiable. If this function inverse function is exist, then it is differentiable. It means that, so we have to find its derivative. Now we take examples. Function f of x equal to x square. We take example. So that is y equal to x square. Now we take its inverse. If this function is 1 1 and onto, then its inverse implies x equal to root y. Now we take the derivative of this both function, this function and its inverse function. Its derivative differentiate with respect to x. So dy by dx is equal to derivative of x square, it is 2x, and here differentiate with respect to y here, because this function x in terms of y and this function y in terms of x. That's why we differentiate this function with respect to y. It is the inverse function. Its derivative of x is dx by dy, and the derivative of root y is 1 by 2 root y. But here root y, this root y is x, and so 1 by 2x, so dx by dy. And so this is the derivative of this function x, inverse function x equal to root y. Its derivative is here dx by dy equal to 1 by 2x, and the derivative of this function y equal to x square is 2x here. And from these two here, these two we write dy by dx is equal to 1 by dx by dy from these two, because this function derivative of the inverse function is the inverse of the original function. It is a dy by dx. So this is the concept of derivative of inverse function. Actually the derivative of these derivatives are the reciprocal of each other. Now we take a theorem which is depend on the derivative of the inverse functions. So statement of the theorem: suppose y equal to f of x is a differential function of x on an interval I, and y is 1 1 and on 2, and dy by dx is not equal to 0 on interval I. Also, if f inverse of y is differentiable on f of I means interval, then we have to prove this. Derivative of f inverse of y with respect to y is equal to 1 upon f dash x. 1 upon f dash x means derivative of f of x, or derivative of x with respect to y is equal to 1 upon its inverse dy by dx, where dy by dx is not equal to 0. Now we take proof here. So here also given y equal to f of x is a differential function of x, and also x equal to f inverse y, these are the differentiable functions. Suppose or given y equal to f of x and x equal to f inverse y are the differential function, are differentiable functions. Now we consider here the delta x, which is increment in x, and delta y corresponding, its corresponding increment delta y in y. Let delta x be the small increment means change in x, then correspondingly delta y is a small increment in y. As delta x is a small increment in x, then correspondingly delta y is a small increment in y here. Now as delta x and delta y are small increments, therefore delta x is non-zero and also delta y is non-zero. Now we have to consider here, we take the ratio delta x upon delta y into delta y upon delta x is equal to 1 here, because delta x will get cancelled and delta y will get cancelled, it gives 1. So we take this ratio. Now we take this term in the right hand side, delta x upon delta y is equal to 1 upon delta y upon delta x, and where delta y by delta x is non-zero, because when we take it 0, 1 by 0 is not defined, that's why where delta y upon delta x is non-zero. Now taking limit as delta x tends to 0 on both sides, we get limit of delta x upon delta y, limit as delta x tends to 0 is equal to limit of 1 upon delta y upon delta x, where limit as delta x tends to 0. Now as this delta x and delta y, as delta x is not equal to 0 and delta y is non-zero, so in the left hand limit, so we change this here, because here the limit of delta x upon delta y, where the derivative of this function x with respect to y here, and the interval of this limit is delta x tends to 0, that's why we change here interval, we take delta y tends to 0 here. Instead of delta x, we take delta y tends to 0. Limit of delta x upon delta y as delta y tends to 0. And in the right hand side, 1 upon limit of delta y upon delta x as delta x tends to 0. Here the derivative of y with respect to x here. That's why interval of this limit is delta x tends to 0. We call this equation number 1. Now, so we have to given y equal to f of x is a differentiable function of x, as since y is a, we'll take this side, since y is a differentiable function of x, it means that by using Leibniz notation, limit of delta y upon delta x, limit as delta x tends to 0, it gives dy by dx, means derivative of y with respect to x by using Leibniz notations. And also given, and this delta y upon delta x is non-zero, so we have to given here. So from equation 1 here, from equation 1, we use this in the right hand side of this equation 1. From 1, from equation 1 and 2, call is second equation. From equation 1 and 2, so equation 1 is in the left hand side, limit of delta x upon delta y, limit as delta y tends to 0 is equal to, in the right hand side here, 1 upon, instead of this limit of delta y upon delta x, we write here dy by dx from by using 2. It is 1 upon dy by dx from 2. Call equation number 3. Now, in the right hand side, equation of 3, limit is exist and finite. Since RHS of this equation 3 is exist and finite, also LHS of this equation 3 is exist and finite, and this equal to dx by dy by using Leibniz notation. As RHS, limits on RHS here, limits on RHS of RHS of equation 3 exist and finite, therefore, or hence limit on LHS of equation 3 also exist and finite. This means that its limit of delta x upon delta y as delta y tends to 0, it gives dx by dy, because the right hand side limit of this equation 3 is exist and finite, and that's why in the left hand side limit also exists and is finite. And so therefore from equation 3 here, we write this limit is equal to dx by dy, means delta of x with respect to y, dx by dy is equal to 1 upon dy by dx. And so this is the derivative of inverse function. So dx by dy is equal to 1 upon dy by dx. Here we prove dx upon dy, derivative of x with respect to y is equal to 1 upon derivative of y with respect to x. It's inverse. It's inverse. Hence proved. Now an alternative proof here. This is already given to in your textbooks, already prove there, so you may copy there this alternative proof of derivative of composite functions. Now we take derivative of standard inverse trigonometric functions. So first function, inverse function, is if y equal to sine inverse of x, where x is less than or equal to 1 and greater than or equal to -1, and y, function y is less than equal to pi by 2 means 90 and greater than equal to minus pi by 2, then prove that its derivative means derivative of y means sine inverse of x. It's inverse, first inverse trigonometric function. So its derivative is here 1 upon root of 1 minus x square, and where x is modulus of x is less than 1. So we take proof here. So given y equal to sine inverse x, where x is less than equal to 1, greater than equal to -1, and also y is less than equal to pi by 2 and greater than or equal to minus pi by 2. So from this y equal to sine inverse of x, we have x equal to sine y, x equal to sine y. Differentiate with respect to y here, because the trigonometric function sine, whose variable is y here, x in terms of y. So derivative of x with respect to y is dx by dy is equal to derivative of sine y with respect to y is cos y, is cos y. Now we write this cos y in this way also. Cos square y. Also we can write this cos square y or square root of, that's why it is plus or minus root of 1 minus sine square y here, because by using first trigonometric first identity here, first identity is sine square y plus cos square y equal to 1. By using this first identity, so we may write cos square y is equal to 1 minus sine square y. Now from equation 1, here the sine y is x here, so that's why we write 1 minus x square. The sine y is x. Now but here y is cos y is positive, cos y is positive as y lies in first or fourth quadrant. First or fourth quadrant. And therefore, also we have to give one y is less than equal to pi by 2 and greater than equal to minus pi by 2. That's why it is a positive. So we take dx by dy is equal to plus root of 1 minus x square. Now by using inverse theorem, so we write this here, or we have here, we know the theorem dy by dx is equal to, take its inverse, is 1 by dx by dy. By using this theorem, we write this term dy by dx is equal to 1 by root of dxy by dy, means here it is the root of 1 minus x square. So it is 1 by root of 1 minus x square, and hence we have to prove the derivative of y with respect to x is 1 by root of 1 minus x square. Means here the derivative of sine inverse x is 1 upon root of 1 minus x square. So in this way you may copy the remaining inverse trigonometric function from the textbooks. In the textbooks already proof of this inverse remaining trigonometric functions already given. In this way the derivative of standard inverse trigonometric functions are, so first trigonometric function sine inverse of x, its derivative is 1 upon root of 1 minus x square, condition modulus of x is less than 1 here, and condition is x is less than equal to 1 and greater than equal to minus 1, y is less than equal to pi by 2 and greater than equal to minus pi by 2. This trigonometric inverse function we have to already proved here, and the remaining cos inverse function is cos inverse x, its derivative is minus 1 upon root of 1 minus x square, and modulus of x where is less than 1. The derivative of sine inverse x and the derivative of cos inverse x is the same, there is only change here is minus sign, and condition is x is less than equal to plus 1 and greater than equal to minus 1, y is less than equal to pi and greater than equal to 0. Now the third trigonometric function tan inverse x, its derivative is 1 upon 1 plus x square, condition x is a real number, x belongs to R, and y is less than equal to pi by 2 and greater than equal to minus pi by 2 here. Now the fourth trigonometric function inverse function cot inverse of x, its derivative is minus 1 upon 1 plus x square, condition x is a real number, x belongs to R, and y is less than pi greater than 0. Again here the derivative of tan inverse x and cot inverse x is same, but there is a change in only sign. The derivative of cot inverse x is minus 1 upon 1 plus x square, and the derivative of tan inverse x is 1 upon 1 plus x square. Now next inverse function, sec inverse function, its derivative is 1 upon x into root of x square minus 1. For x is greater than 1, it is positive. Condition is modulus of x is less than equal to 1 and y is less than equal to pi and greater than equal to 0. And last trigonometric inverse function cosec inverse x, its derivative is minus 1 upon x into root of x square minus 1 for x is greater than 1, and condition modulus of x is greater than or equal to 1 and y is less than or equal to pi by 2 minus pi by 2. In this way, these are the 6 inverse trigonometric function and its derivative. So in this way, this derivative of inverse trigonometric functions whose letter is C, its derivative is minus. Cos inverse of x is minus, cot inverse of x is minus, cosec inverse of x is minus 1. Now we take some important formulae for inverse trigonometric functions. So we have to use these formulae when we solve exercise 1.1, example of inverse trigonometric functions. So here first, sine inverse of sine theta, it use theta. Whenever in our example sine inverse of sine, then it is only angle of this sine, it is theta. Also here sine of sine inverse theta is also theta. It is same as sine inverse of sine theta or sine of sine inverse theta, it is only angle of this bracket trigonometric functions. Same way next, second, cos inverse of cos theta, it is theta. Again cos of cos inverse theta, it is also theta. Then tan inverse of tan theta, it is also theta. Tan of tan inverse theta, it is also theta. Now cot inverse of cot theta, it is theta. Again cot of cot inverse theta, it is also theta. And sec inverse of sec theta, it is theta. Sec of sec inverse theta is also theta. And last 6, cosec inverse of cosec theta is theta and cosec of cosec inverse theta is equal to theta. Now whenever our function is a sine inverse of cos theta and we have to convert this cos theta into sine by using this formula. We have to convert this formula into this. So we take here cos theta, we convert this cos theta into sine by using this allied angle 90 minus theta, pi by 2 minus theta. So sine pi by 2 minus theta is cos theta, and then after that we use this formula sine inverse of sine of angle, sine inverse of sine pi by 2 minus theta means theta, it is only theta. So it's theta, its angle of this sine is only pi by 2 minus theta. Again same, cos inverse of sine theta, whenever we convert this sine theta into cos theta by using allied angle, so sine into cos, so it is cos of pi by 2 minus theta, and so it is cos inverse of cos theta, second formula. By this second formula, cos inverse of cos theta, it is angle theta only, means cos inverse of cos pi by 2 minus theta, this is the angle of this cos, is only pi by 2 minus theta. Same way tan inverse of cot, so we have to convert this cot into tan, so by using allied angle which is pi by 2 minus theta, pi by 2 minus theta. So tan inverse of tan theta, it is again by using third formula, it is the angle of this tan only, pi by 2 minus theta. Next, cot inverse of tan theta, again we convert this cot into tan into cot here because cot inverse here. So again by using allied angle we convert this tan theta into cot by pi by 2 minus theta, and so it is cot inverse of cot theta by formula number 4, it is theta only, theta means here it is pi by 2 minus theta. Same way sec inverse of cosec theta is, again we have to convert this cosec into sec by using allied angle pi by 2 minus theta, and so it is a sec inverse of sec pi by 2 minus theta. It is only angle of this pi by 2 minus theta by using this fifth formula. Now 12th number, cosec inverse of sec theta. So we have to convert this sec theta into cosec. So it is a cosec by using allied angle pi by 2 minus theta. Cosec pi by 2 minus theta, it is a sec pi by sec theta. And so again we use this sixth formula, cosec inverse of cosec theta. It is only angle of this cosec. And so cosec inverse of cosec pi by 2 minus theta, its angle pi by 2 minus theta only. Now whenever in the next formula, formula number 13, sine inverse of x. So we have to convert sine into cosec. It's reciprocal. So in our trigonometric function, reciprocal of sine is a cosec. Same way, in inverse, sine inverse of x, its cosec, its inverse is cosec inverse of 1 by x. In inverse, take its reciprocal of x also. Take is it reciprocal of trigonometric function also. Take its reciprocal of angle of trigonometric function. Reciprocal of x is 1 by x and reciprocal of sine inverse is a cosec inverse. Same way, reciprocal of cosec inverse x is a sine inverse of 1 by x, because reciprocal of sine is cosec, that's why it is 1 by x. Same way, cos inverse x, its reciprocal is a sec inverse, and take reciprocal of angle of cos is 1 by x. Same way, and the next sec inverse x, so its reciprocal is again cos, and take its reciprocal of x is 1 by x. Then next tan inverse x, we write in this way, cot inverse by again into 1 by x. So tan inverse of x, we write reciprocal, it's reciprocal, then it is a cot inverse of 1 by x. Same way, again we write the reciprocal of this cot inverse x is tan inverse 1 by x. You may write the reciprocal of this standard trigonometric function and takes also its reciprocal of angle x 1 by x. Next, formula number 19, sine inverse of x plus cos inverse of x is pi by 2. So addition of this inverse function is pi by 2. Again here tan inverse of x plus cot inverse of x is pi by 2. The next, sec inverse of x plus its reciprocal cosec inverse x is pi by 2. Means here addition of trigonometric function and its reciprocal is pi by 2. Or yes. Next, tan inverse of x plus tan inverse of y is tan inverse of x plus y upon 1 minus x into y. In this formula, there is plus sign, again here is also plus, in the denominator there is minus sign, there is change in only. Whenever here it is plus, in the denominator 1 minus xy, and whenever it is minus, then in the denominator 1 plus xy. Then next formula, tan inverse of x minus tan inverse of y is the tan inverse of x minus y upon 1 plus xy. Angle of tan is x, angle of tan is y, so x minus y upon 1 plus xy. So these are the important formulae for inverse trigonometric function. We use these formulae in exercise 1.2 whenever we solve this exercise 1.2. In this way, you take screenshot of this formulae, and in this way today we stop here.